All right, everyone, we're looking at Chapter 7, Section 7.3, Sample Means. And you'll notice a lot of these are very similar to Section 7.2, which was sample proportions. All right, so as you're going through, it might be a good idea to see the similarities between the two, but also the differences between sample means and sample proportions. And I'll try to highlight some of those differences as well. But don't just watch this video for 10 minutes and assume, oh, this is everything. I already know all this from last video. It is a difference. We are looking at sample means today, not just sample proportions. So by the end of this learning target, or in this video, your learning target should be calculate the mean and standard deviation of the sampling distribution of a sample mean x bar and interpret the standard deviation. Explain how the shape of a sampling distribution of x bar is affected by the shape of the population distribution and the sample size. Calculate the mean and standard deviation of the sampling distribution of a difference in sample means and interpret the standard deviation. Determine if the sampling distribution of the difference in means, which is x bar 1 minus x bar 2, is approximately normal. If appropriate, use a normal distribution to calculate probabilities involving x bar or x bar 1 minus x bar 2. So the sampling distribution of x bar, which is the sampling distribution of the sample means, that's what x bar is, sample means, describes the distribution of values taken by the sample mean x bar in all possible samples of the same size from the same population. So here's an example. Also consider our example that we did with the pennies activity. We made multiple approximated sampling distributions. So here they are doing the approximate sampling distribution of the sample mean year of pennies in 50 samples. So they did it 50 times of size 5 and then size 20. We did it in class, we did size N was 4 and our N 32. Those were slightly different, but they look similar. And now recall that each dot here on this dot plot is really now a sample mean. That's why it's labeled as X bar. It doesn't have to be labeled as an X bar, but they're just doing that to show you, hey, these really are sample means. They're no longer just a dot. So sampling distributions of X bar, the mean and standard deviation. Suppose that X bar is the mean of an SRS of size n drawn from a large population with mean, mu, and standard deviation sigma. So then the mean of the sampling distribution x bar, which is so the mean or the mu of x bar is going to equal mu. So the mean of the sampling distribution equals the mean. And the standard deviation of the sampling distribution x bar follows this formula, which is the original population sigma over the square root of n. Right? Now, this only works as long as the 10% condition is satisfied, which means that, hey, the sample size is less than 10% of the population size. That is the same thing for proportions, all right? You still have to check that 10% condition, or you have to take independent random samples. So in our pennies activity, if we took a sample, put them all back, and then took another sample, now they're independent, all right? And we're sampling with replacement, so you don't have to worry about the 10% condition. But if you don't know, if it is not with replacement, you do have to check the 10% condition for either type of sampling distribution, right? And just like before for proportions, the value sigma x bar measures the typical distance between a sample mean and the population mean. So before for proportions, it was the sample proportion and the population proportion. Here it's the sample mean and population. So here's what I was just kind of highlighting about that 10% condition. If you're sampling with replacement, the standard deviation of the sampling distribution is exactly sigma over square root n. If you're sampling without replacement, the observations are not independent, and the actual standard deviation of the sampling distribution of x bar is smaller than the value given by the formula. So if the sample size is less than 10% of the population size, then this difference is basically nothing, and you don't have to worry about it. And so that's why you just check the 10% condition. If they are not independent, or if they are sampling without replacement, check the 10% condition. If it passes, if the sample size is less than 10% of the population, you are good to go. All right, here's an AP exam tip that a lot of kids mess up on, that notation does matter. The symbols p hat, x bar, n, p, mu, sigma, they're the mean of the p hat, the standard deviation of the p hat, the mean of the x bar, and the mean and the standard deviation of the x bar, all have specific and different meanings. So you either use the notation correctly or don't use it at all. If you don't use it, make sure to verbally use it. Explain. So you're talking about the mean of the sampling distribution for means, that is mu x bar. Right? That is the mean of the sampling distribution for x bar. So if you use them incorrectly, just be prepared to lose some points. So you should be doing enough problems with the homework that it becomes common um, which notation to use. So just be careful of that as you're working on your free response questions. All right, so here is a sampling distribution of X bar. The number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies and a standard deviation of 15.8. Suppose we take an SRS of 100 students from this school and calculate the mean number of movies viewed by the members of the sample. Identify the mean and the sampling distribution of X bar. Identify the mean of the sampling distribution of X bar and calculate and interpret the standard deviation of the sampling distribution of X bar while verifying the 10% condition. So the mean of X bar is just equal to the mean of the population, which is 19.3 movies. And so now we got to check the 10% condition because we're sampling without replacement. So we're assuming that 100 students is less than 10% of all the students at the large high school. If you're at a large high school, I think it's pretty safe to assume that there are over 1,000 or 2,000 kids in it, so we are good there. So since the 10% condition is met, we can go ahead and use that sigma x bar is approximately sigma over square root n. So 15.8 divided by square root of 100 comes out to 1.58 movies. Now to interpret that, that means in SRSs of size 100, the sample mean number of movies viewed will typically vary by about 1.58 movies from the true mean of 19.3 movies. We have described the mean and standard deviation of the sampling distribution. All right, the mean of the sampling distribution for means is just mu, and the standard deviation of x bar is just standard deviation over square root n. All right, but we haven't talked about the shape, and that's because the shape of the sampling distribution of x bar depends on the shape of the population distribution. So here at the top is the population distribution. It's normal. All right. Now, if we take samples of size 5, like here's my sample 1, 2, 3, 4, 5. So this is the population distribution. This is a sample distribution. And then down here is a sampling distribution. Each one of these bricks is a sample of 5. All right. And so what this shows is if your normal distribution is normal, if your population distribution is normal, then the sampling distribution will also be normal regardless of the size of the sample. Like here my sample is 5, which is really small, but it doesn't matter because the population distribution is normal. So as long as the population distribution is normal, then the sampling distribution will also be normal, regardless of the size. Right? So suppose that the population of a normally suppose that a population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of x bar has the normal distribution with mean x bar equaling mu, the standard deviation of sigma over square root n, provided that the 10% condition is met. And it has a normal distribution. It is a symmetric normal distribution because the population was normal. All right, so let's do an example now. The heights of young women follow a normal distribution with mean 64.5 inches and standard deviation 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. And this is find the probability that the mean height of an SRS of 10 women will exceed 66.5 inches. So first things first, this is if it's just one individual, right? One individual, 66.5. And we treat this like we did at the beginning of the year. Hey, you could use any one of these. You could find your z-score and then use your table, or you could just use technology. I would jump down right to the bottom one. Hey, normal CDF. My lower, where I want to see if they're bigger, is it taller than 66.5 inches. So lower is 66.5, upper is 1,000, mean is 64.5, and standard deviation is 2.5. All right. So that comes out to 2.2119. Okay. So you don't change the mean or standard deviation at all because it's just one person. Now for part B, though, we are sampling a group of 10 young women, and we're seeing if their mean height will exceed 66.5 inches. So with that, my mean of my sampling distribution is equal to mu, so it's still 64.5. Our 10% condition is met because it's the height of young women. So all women in the world, there's certainly more than 10%, or 10 is certainly less than 10% of all women and young women in the world. So that's met. So now our standard deviation for X bar is 2.5 divided by square root of 10. So because the population of heights is normal, the distribution of X bar is also going to be normal. If the population is normal, it doesn't matter what our sample size is. So with that, we're going to jump to the normal distribution using mean and standard deviation. So again, I'm going to jump right to the bottom. Hey, my mean, my lower is 66.5. My upper is 1,000. My mean is 64.5, and my standard deviation is 0.75. All right. Versus, so I get that out to be 0.0057. So versus if it's just one person is 0.2119. And that kind of makes sense, right? Because if you just pick one person out, the probability of them being bigger than 66.5 inches is larger than if you pick 10 people and you want their average height to be bigger than 66.5. It's a lot harder to get the average of 10 people to be larger than one number than just one person alone, right? Because you need to have more consistency with it. So it's a lot easier if just the one person is being picked than if 10 people are being picked. All right. So now looking at that sampling distribution of a normal population, the reason why those differences also occur is your standard deviation is different, right? Looking here, my standard deviation is 0.719, and up above before in part A, my standard deviation is 0.2119. Oh, no, sorry. My standard deviation is 2.15, 2.5, 2.5. Yeah, 2.5 versus 0.79. So when I look at the normal distributions, this purple one is a population distribution. Yes, it's normal, but it has a standard deviation of 2.5, so it's a lot spread out and a lot flatter than the sampling distribution of X bar, which had a standard deviation of 0.079 or 0.79. It pulled it in a lot more. So they're still both normal, follow normal distributions. However, this one is a lot smaller of a standard deviation, so it's a lot narrower versus the purple one, which has a larger standard deviation, so it's a lot flatter. And so that's the difference between the two. However, they're both still normal. And since they're both still normal, we can still use the normal distribution for both. Right? Now, many students lose credit on the probability calculations involving X bar because they forget to divide the population standard deviation by square root n. Remember that averages are less variable than individual observations. So that's another reason too, right? Yes, the standard deviation is a lot larger for one person. That's why it's so spread out. Versus for 10 people, it's going to be a lot harder to vary more. Your standard deviation is going to be smaller. All right. So now we're looking at the central limit theorem. All right. And this is kind of a big part. It kind of goes along with it. This mimics the large counts condition for proportions. All right. So what the central limit theorem says that most population distributions are not normal. And so here are the approximate sampling distributions of X bar. So with size n equals 2 and n equals 25. Well, I don't know what's going on with all these video things. So if I had a uniform distribution, a skewed right distribution, or a bimodal distribution, right? If I took samples of size 2, My uniform distribution kind of looks normal, or at least looks symmetric, but maybe not normal. My skewed right distribution with mean of 2, it still seems skewed right, and this binomial thing looks all kind of funky. However, when my sample size goes up to 25, my my distribution looks a lot more normal, a lot more normal, a lot more normal. It doesn't matter what my parent population is, as long as my sample size is large, my sampling distribution is going to become more and more normal the larger and larger my n goes. So when n is 2, not very normal. When n gets to 25, it's more normal. And as n goes even bigger and bigger, it's going to follow a normal curve even more and more. So the central limit theorem basically states that drawing an SRS of size n from the population with mean mu and finite standard deviation, the central limit theorem says that when n is large, the sampling distribution of the sample means x bar is approximately normal. So there's two conditions for shape. If the population distribution is normal, the sampling distribution of x bar will be normal regardless. It doesn't matter what size n is. If the population distribution is not normal, the sampling distribution of x bar will be approximately normal when the sample size is large enough. We will consider n to be greater than or equal to 30 to state if it is large enough. Okay, if the sample size is small, the population distribution is not normal, and the sampling distribution will retain some characteristics of that distribution. Think about this one here, right? N is small, N is just 2. It has a similar distribution as the parent one. It's still going to be skewed right. So here's a problem with central limit theorem. Keith is the manager of an auto care center. Based on service records from the past year, the time and hours that a technician requires to complete a standard oil change and inspection follows a right skewed distribution with mu equals 30 minutes and sigma equals 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem that offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? So I'm going to calculate the probability that the average time it takes to complete work exceeds 35 minutes. So that's just for one. Sorry, that is based on the 40 people. So my mean of x bar is going to be 30 minutes. It's going to be equal to mu. 40 is less than 10% of all current customers, so it's okay. So it meets the 10% condition. So I'm going to go ahead and use that sigma of x bar as 20 because that's how long my sigma is. 20 divided by square root of 40 gives me 3.16. So because the sample size is large, 40 is greater than or equal to 30. That meets the central limit theorem. The distribution of x bar is going to be approximately normal. So I can now go ahead and use that. I'm going to have my mean is 30, my standard deviation is 3.16, and I know I'm approximately normal. I am, again, going to jump right down to the bottom. Hey, I want to see calculate the probability that the average time it takes to complete the work exceeds 35 minutes. So it's larger than 35 minutes. So that means my lower bound is going to be 35, my upper bound is going to be 1,000, my mean is 30, and my standard deviation is 3.16. So that occurs just 5.68% of the time. So there's only a 5.68% probability that Keith hasn't budgeted enough time to complete the work. So pretty good, but he might want to do better than that, than just 5% messing up. So part B asks how much average time per customer should Kenneth budget if he wants to be 99% certain he doesn't go over the budget. So he wants to make sure that he is under budget 99% of the time. So basically, we're going to look for what that cutoff point is. How much time do we need to spend so that we do not go over 99% of the time? So since I'm going to go from the left up, I want the area of my curve to be 99.99 for 99% of the time. All right, so my area is going to be 0.99. That means I'm going to use inverse norm, which is my area, 0.99. Remember, inverse norm always goes left to the cutoff point. My mean is 30, and my standard deviation is 3.16. Get it out, I should budget 37.4 minutes in order to never go over, or to not go over 99% of the time. or he's not 99% of the time, but he to not go over 99%. Sorry, he wants to be 99% certain. Remember, it's not guaranteed that it will happen 99% of the time. So that's like the law of large numbers. He'd have to do this promotion lots and lots and lots of times in order to satisfy that 99% won't go over. But he's 99% certain he won't go over based on if he accounts for each inspection to take 37.4 minutes. And so to be 99% sure he has budgeted enough time, Keith, I don't know what I was thinking, Keith should plan for an average of 37.4 minutes per customer. All right. And now the last kind of subsection would be sampling distributions of a difference between two means. The heights of 10-year-old girls can be modeled by normal distribution with mean 56.4 inches and standard deviation 2.7. The heights of 10-year-old boys can be modeled by normal distribution with mean of 55.7 and a standard deviation of 3.8. So suppose we take independent random samples, girls of 12 and boys, and 8 boys, sorry. SRSs of 12 girls and 8 boys, and measure their heights. So these are their distributions. The girls the sampling distribution of the girls' average height of 12 girls per sample is going to be approximately normal because the population distribution is approximately normal. We don't need to do central limit theorem because my population comes from a normal distribution. The center is going to be 56.4 inches, and the standard deviation is going to be 2.7 divided by the square root of 12, which is 0.78. We can use this formula because 12 is less than 10% of all 10-year-old girls in the United States. Right. For the boys is also approximately normal because the population distribution is approximately normal, so that's not going to change. Again, don't need central limit theorem. My mean is 55.7 inches, and my standard deviation is going to be 3.8 divided by square root of 8. So again, boys, there's 8 in my sample, and girls, there are 12 in my sample. And again, because 8 is less than 10% of all 10-year-old boys in the United States, we are good to go with that formula. So what can we say about the difference between girls minus boys? Well, here's the sampling distribution for girls and boys. So we took all the samples, we took the girl samples and the boys, and we paired them up 1 and 1, found the difference. So that red dot right here, that is one set of samples. That's a girl sample and a boy sample. Subtract them away at 1.41 inches. And that's what that red dot represents. It's one set of samples of girl minus boy. All right. Now, the mean of this distribution of girl minus boy, the sampling distribution of the average or the mean girls minus the mean boys is going to be just 0.7. You just subtract their means and they keep going. All right. Remember, think about combining random variables. Means always behave the same way. When you subtract them, you subtract their means. With their standard deviations, though, you have to take the variances and then take the square root. Now this looks a little bit different, but remember the formula. It was sigma divided by square root n. So we find the variance, we square that. That would make my sigma squared over just n. And then I combine the variances, I always add them. So that's sigma squared over n plus sigma squared over n. I add them together, and then I take the square root. That's how I get my standard deviation. All right. The reason why we were able to do that again, remember, we were able to use the formula first off because the distribution, because the sample sizes were less than 10% of their respective population sizes. So we were able to use the formula. And the girls sample and the boys sample, there is no, they are independent of each other. So that's why we can combine these variances together. Remember, you can only add, or you can only find the standard deviation of random variables if they are independent of each other. Same thing here. You can only find the standard deviation of sampling distributions if their samples are independent of each other. All right, so if you choose an SRS of size n1 from population 1 with mu1 and standard deviation sigma 1, and an independent SRS of size n2 from population 2 and mean 2, standard deviation of sigma 2, then the sampling distribution is normal if both population distributions are normal, or it is approximately normal if both sample sizes are large which means that they're both larger than 30. If one population is normal distributed and the other sample is large, then it is also just normal. So either has to be normal or it has to be approximately normal based on the central limit theorem, which means n is bigger than 30. The mean, they're just going to behave like you do. You subtract mu1 minus mu2. And the standard deviation, this is the formula that can get a little tricky. It becomes sigma squared over n plus sigma squared over n. Take the square root of that. And again, that only works if the samples are independent and if the 10% condition is met for both samples. All right. This is what I just highlighted there. They have to be independent samples in order to combine them, and then they have to be independent observations. So within each sample, there has to be independent as well, or which means with replacement, or if it's not with replacement, you have to check the 10% condition. So here's one more example. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27 ounces and a standard deviation of 0.4 ounces. When the medium setting is chosen, the amount of liquid M follows a normal distribution with mean of 17 ounces and a standard deviation of 0.5. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled using the large setting and 25 cups filled using the medium setting. Let x bar L minus x bar M be the difference in sample mean, the amount of liquid under the two settings. So what is the shape of the sampling distribution? The shape is going to be normal. All right, that's because both populations came from normal distribution. All right, so although my n's are less than 30, since they both come from a normal distribution, then the combined sampling distribution will be normal. All right, find the mean of the sampling distribution. Again, you are just going to subtract their means together. So x bar large minus x bar medium. 27 minus 17 gives me just 10 ounces. And then calculate and interpret the standard deviation. And you're going to combine their variances. So it's going to be 0.8 squared over 20 plus 0.5 squared over 25. Add them together and take the square root, and we get out 0.205 ounces. Now, we did not have to check the 10% condition here, just like we didn't have to check the large counts condition for the shape because those were normal. Here we don't have to check the 10% condition because we are not sampling without replacement from a finite distributed population. We just are taking samples. There is no need for replacement. We essentially are replacing it each time. Each time has its own independent trial, so it doesn't affect it. All right, so now calculate and interpret the standard deviation of the sampling distribution. Oh, so just to interpret the difference between large cups minus medium cups in the sample mean amounts of liquid typically varies by about 0.2 ounces from the true difference in the means of 10 ounces. All right. And now lastly, we're going to estimate the probability that the difference is within 0.25 of the true difference. So if you're within 0.25 of the true difference, that means you're above 0.25 or below 0.25. So my true difference is 10. So to be above and below by 0.25 is 0.75 or 9.75 to 10.25. Again, I would jump right to the normal distribution. Lower equals 9.75, upper is 10.25. I'm finding the area between those two with a mean of 10 and a standard deviation of 0.205. And that's how you get it out. And those are your learning targets for this section. Hope you enjoyed.